Okay, so here we're going over recurrent neural networks, and hopefully we'll get through all of these slides. We might not, we shall see. So again, this is for the week of the 26th, we're going to have like the beginning of our neural network talk, and we had that refresher that I posted, right? So here's the beginning of our neural network discussion, recurrent neural network discussion. Actually, yeah, let me, as I usually do, write. Unit 8, current neural networks, and the long short-term memory. All right, so, and you may have heard my cat sneeze. Hello, Gracie. By recurrent, we mean a network where one unit connects back to itself, right? So we've seen a bunch of networks where information flows from unit to unit. A recurrent network is a network where a unit connects back to itself, or potentially back to a previous network. In the broadest sense, right, it could just be sort of any not forwards flow. But for our purposes, we mean a network where a unit connects to itself. So saying that is technically correct, and you'll often see it defined that way at first, but it doesn't really describe what the network does, right? So just saying it connects back to itself doesn't tell you how to compute that output, right? It tells you nothing about what the math looks like, what the code looks like, or how this new modified network behaves. And in fact, there are a bunch of different ways that we could interpret this, right? Excuse me. And I've linked to a big overview on Scholarpedia that lists many ways that you can, like many types of neural networks, right? So networks that loop back is a massive category with many different meanings. What we care about in a sort of machine learning context is a network that gets some part of its previous state when computing the next state, right? So the inputs are ordered, right? That's supposed to be a T, but it came out kind of like a plus, right? So T minus 1, T plus 1, right? The states are ordered, and when the unit is producing the output for time t, it gets the input for time t, but also the output of the previous state at time t minus 1, right? So the input x of time t comes in on this connection, and the previous output, I don't know why I put that there, is coming in on this connection. So the node, when it computes the output for time t, it gets both x of t and the previous output for time t minus 1. Okay? So the network is, or can learn to, keep a kind of memory or state that it carries forward from sample to sample to sample, from iteration to iteration to iteration, so that it can be time aware, right? Or maybe sequence position aware, right? So it ends up having a kind of memory or state that it gets to store from across the elements of a sequence, and it is time aware, right? So unfortunately, we talked a little bit about this with the CNN stuff, that convolutional networks, a lot of the terminology there is not very precise, and it gets used in different ways. Unfortunately, that's still kind of true. Some people use the term RNN, writing mode, there we go. Some people use the term, and as usual, okay. As usual, while I'm fiddling with the pen controls, it starts jumping from slide to slide at random. So some people use RNN to mean an Elman network. And we're going to talk about that in a minute, right? An Elman network is the thing we're going to pick as our generic, simple RNN, okay? So sometimes people use RNN to mean an Elman network, more or less. Other times they use it in its more technical capacity to mean any network with a recurrent connection, which again is a huge category, right? There are many, many, many networks that fall under that definition that are wildly different, all right? So when I use RNN, so when I use these terms, I'm going to try to be very careful to use just RNN without any kind of qualifier to mean the huge wide open family of any kind of recurrent network. I'm going to use the more specific terms vanilla RNN, simple RNN, fully connected RNN to mean an Elman network more or less, right? Where again, Elman network more or less is our generic, simple network. And it is specifically this, right? That is the math for an Elman network more or less. That is the math for our generic, right, simple, vanilla, feed-forward, fully connected, basic RNN, okay? And notice that we've got one weight matrix connected to the inputs, and then another weight matrix connected to the previous output, right? So here is the output for time t. Here is the previous output, the one from t minus 1. Here is the input from time t. We connect both with weights, see? And TensorFlow calls this a simple RNN. And again, this is one of those times when different authors maybe don't fully explain what they're doing, because I had, to go to the code directly to find out that this is in fact what their simple RNN cell does, right? They didn't tell you. They didn't give you the math, frustratingly. They just leave you to guess. And again, this is not surprising. When I looked at the code, I was like, oh yeah, that's what I expected, but still, right? Simple RNN could mean any number of things, and it turned out in TensorFlow that it means this, which is kind of loosely an Elman network. Here is a picture. This is under, variants of this picture abound on the internet. This is maybe not the best one, but it is one that I am able to redistribute to you because I did it, right? It has the advantage of being licensed to me. So we can sort of see graphically, right? We have coming into our sort of Elman, and I just tried to keep drilling this in, right? But Elman-like, Elman more or less, simple RNN cell, right? Simple RNN cell. We have the input at time t and the output at time t minus 1, both going into the input. So it's yielding an output at time t, but it's also storing that output, to be an input at the next step, right? So xt goes in. Well, okay. So I guess x0 goes in, right? But then for some t, xt goes in, and model of t minus 1 goes in, and model of t is produced. And again, we see that we have one weight matrix connecting us to that input, and another weight matrix connecting us to the output. Okay. And this should look like the same neural network math that we've been doing, right? It's just we have this extra recurrent term in here, right? And that is the sense in which this is the simple or simplest sort of default vanilla generic RNN, right? Because if you sort of compare it to the normal feed-forward neural network, right, it has kind of changed the least and in the most straightforward way, right? It has added this recurrent connection and this input from the previous output, and that's it, right? I wrote a sigma here. The output doesn't actually have to be sigma. It could be any activation function. Just a lot of some of the literature uses sigma incorrectly interchangeably with any activation, and some doesn't. All right. So that recurrent state, right? Notice that so basically notice this plus right here, right? So every unit of the output is connected to every unit of the input by a weight wx, and every unit of the previous output by a weight wm, right? So every unit of the output is connected to every unit of the input and every unit of the previous output. Okay? And that's what that plus is telling us, right? Because when we multiply the x weights, the input weights, by the input, right, we get a column vector of preactivations. And then when we multiply the weight, so the weight matrix for the previous output by that output, we get a column vector of activations. Then we add those together, and we apply the nonlinearity to the sum of both of them, right? So it's one set of units that ends up getting solved for here, right? These two different products, one, have to be the same height, right? Have to have the same number of units, and they get added together so that each unit of the output is the sum of these two things, right? And if we kind of want to think about it that way, right, we could write, right, each y in the output, or each y in the preactivation is the result of adding a sort of x preactivation and a previous output activation together, right? So yeah, as a little note, right, x and m do not have to be the same size, but x and m don't have to be the same size, but mt minus 1 and m do, right? And these two matrices need to map both of these products to the same size, right? So this could be, if this thing had 20 output and 30 input, right, then wx, that weight matrix, would have to be 20 by 30, right, because the input is size 30 and the output is size 20, and then wm would have to be 20 by 20. See? Yes? And I do not say this to confuse people. I say this in the hopes that making these numbers concrete will sort of help clarify this for some, right? So these both have to have 20 as the output size because they're getting added together, but they don't both have to have 20 as the input size, right? Because m and x can be different sizes. Yes? So there's a catch here. Notice that there are not special memory cells, okay? Some activations we could, or some recurrent networks we could imagine could have, for example, the feed-forward unit and then a special memory cell, right? We could imagine this, right? The memory unit being separate. That is not the case here. For this simple vanilla feed-forward network, oh no. Right? It just loops directly back to itself, right? With no special memory cell that is separate. That means that the same hidden unit might get used either for a computation, whoops, what am I talking about here? Either for a computation, right? That might be some useful feature in the output that the network wants to use for output, right? For communicating data up, or as memory, right? So some of the output units here might really be getting used by the recurrent layer as a memory, right? And then the following layers might have to learn to ignore that, right? So I guess what I'm sort of getting at here is a little bit like a private variable, right? Some of these things are going to be used for computation that following layers, or computation, right? For computation or output, right? To communicate up information that following layers will need. While at other times, other hidden units, it might learn to use as a memory, and those memories might carry no information useful for following layers, and so they'd have to learn to ignore it, right? And that basically, learning those kinds of behaviors, right? So the RNN layer learning these kinds of behaviors is going to take training time, right? And then potentially learning to ignore a memory unit that doesn't carry useful information will take the higher layers training time, right? So the network can learn like memory and computation as roles for these layers, but it's going to take it time to do that because we haven't biased it towards that, right? We've just given it this very simple generic structure, and we're trusting that it will learn these advanced behaviors on its own given enough time and data. Hopefully, this should remind you a little bit of our discussion of, the limitations of dense networks on images, right? And why we needed CNNs. We're going to have a little bit of a similar thing where we're later going to talk about the long short-term memory, and that's part of why we're going to care. Oh, come on. Right? All right. So yeah, if the network needs to use some of the units for memory and others for computation, it has to learn to do that, and then the following layers have to learn to respond to that. Yeah, I think this might be a good place for a video break.